All right. Okay. So for today, well, there's two parts. Okay. um, One is we are going to do just see an example of the neural network, and we're going to apply it to the Mnist data set. So I'm not sure if you are familiar with this, but on CCLE, I have this link that will take you to download the Mnist data, and this is the original Mnist data set, okay? And it is a database of handwritten digits. There's a training set of 60,000 and a test set of 10,000, okay? It is a subset of the larger set available from the NIST, okay? And the digits have been size normalized and centered in a fixed size image. So it is perfect for like some machine learning things. It's a very, very, very clean data set with nicely formatted pictures that we can use and train a neural network on. Okay, so part of the problem with doing any kind of machine learning these days, there's a huge chunk of time that you will spend having to clean data up. Okay, and we don't have a course dedicated to cleaning data. Like we do a little bit of, we touch on it a little bit probably in 102A with a little bit of data manipulation and summarizing stuff. But when you, um, you know, well, I imagine a lot of you want to apply for machine learning / data scientist type jobs. And, you might be thinking like, oh, so one of my recommendations is you should always make a portfolio of your work. You should create a GitHub account and, do some projects and put your projects on GitHub. That's always part of my recommendation. And, as far as what kind of projects should you do, so my recommendation is don't put on your homework, okay? Okay, so because first of all, you might be breaking some rules there and you could get in trouble for publishing your homework and homework answers. And no employer is impressed if you say, I did my homework. Look at my homework. No one's gonna be impressed by that, okay? Can you imagine applying to college and then they say, well, what are you proud of? And you say, well, I did my homework. Like that's not impressive, okay? But if you've done a project that was outside of anything that anybody has asked you to do, and you said, well, this was something that I took interested in and I did on my own, that's more interesting and that's better. And of course, a project that shows that you are able to take messy data and clean it up and then analyze, and then you can think properly through your analysis, that's going to be key, right? Because rarely in the real world do you have nice, clean data all ready to go, okay? But, for a class like this, it's nice that we can work with some cleaned up data. So the data are these little 28 by 28 images. So let me just show you, if you just search Mnist and you go on Google and you type in images, these are what the pictures look like. They are these 28 by 28 pixel images, okay? So, maybe I'll copy this image here and I paste it right here. That didn't work. Oh my goodness, that is much bigger than I wanted. Okay, let me just do this, okay? So this is what we have. You get these 28 by 28 images, okay? And each of them are labeled. They are all cleaned up so that they're all isolated in these 28 by 28 things, okay? And what these are all like the problem kind of originated with the post office, and they wanted a way to automate the sorting of mail, okay? Just because, you know, in the US, you write these zip codes, and based on the zip code, it will send it to a different part of the country. And, you know, sometimes people will write the address by hand, and those had to be sorted manually. Somebody would have to look at it and say, okay, this is, you know, 90210. So we're going to send it over here, and this one is zip code, you know, 00578, and it's going to go over here. And somebody would have to look at that, and they wanted to automate this using machines. And so to train it, they scanned all of these handwritten zip codes, and then they isolated each digit into this 28 by 28 thing, and then they grouped them all together, and they said these ones are all zeros, and these ones are all ones, and these are all twos and threes and fours and things like that. And they were, you know, they're able to label all of these things. And so now we have this huge, very clean data set that we don't have to do really any kind of pre-processing for doing it, okay? So we can just go straight to the machine learning. And again, in real life, it's never this easy. You generally have to spend a good amount of time cleaning up your data before you can throw it into a neural network. But here, the data is clean and it's ready to go. And what we're gonna do is we are going to take our 28 by 28 image, and we are going to turn it into a vector, okay? And there's a beautiful little animation in this 3 blue 1 brown video that shows
ones with a given digit. There's also a
okay, so here is the 28 by 28 image, and what we're going to do is we're going to turn it, so there's 784 values inside this inside the each entry is this 28 by 28 pixel image, and each pixel, you know, is a number that in this case it goes from 0 to 1, or I think in our case it goes from 0 to 255, but we're going to divide everything by 255, so it goes from 0 to 1. And
all of these 784 neurons make up the first layer.
I don't know if you guys are able to hear this. Are you able to hear the sound when I play it? Okay, so we're going to go ahead. All right, so this little image, or this animation, I think is a beautiful representation of what's happening, okay? So
all of these 784 neurons make up the first layer of our network.
Okay. And so we're going to take the 28 by 28 things, and we're just going to turn them into a straight vector of 784 values, okay? And each of those values, again, here, let me rewind,
will be input image,
value from 0
which is
to
784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network. Now jumping over to the last layer, this...
Okay, so Grant and 3 blue 1 brown creates a neural network with 2 hidden layers, okay? I'm gonna simplify this, but we're gonna have the input layer, 784 neurons, and then we're gonna have, or 784 nodes, and then we're gonna just have one hidden layer, and I'm arbitrarily just picking 30, okay? Just an arbitrary number. You know, you want 100, you can do 100. You want 10, you can do 10. I'm arbitrarily picking 30, okay? And so that's gonna be kind of what my neural network is gonna look like. So I'm gonna kind of cheat and take this part of the image, and then take 30 nodes in the hidden layer. Okay, so our neural network is only going to have one. There we go. Okay, so now this is a little bit more of our representation. So we've got 784 nodes in our input layer. All right, so this is our input layer, and this is our hidden layer. Okay, and I've arbitrarily picked 30. Okay, 30 nodes, and this is an arbitrary decision. There's no. How do we know how many nodes we should pick in the hidden layer? We don't. How many hidden layers should we have? How do we know how many hidden layers we should have? We don't know, okay? It's a little like the architecture of a neural network is not very well understood, okay? We know that for deep learning, you can, if you have like 100 hidden layers, you can get really good performance. But it also takes a lot longer to train. And but yeah, how many nodes should you have in each one? We don't really know, okay? And then what we will also see in the video is we're gonna have 10 nodes in the output layer. Okay, does performance always increase with increasing hidden layers? No, it's mind-boggling, but no, there's no like, you can have 30 nodes and have good performance, and then you can go up to 100 nodes and have worse performance. You can have one hidden layer and increase the number of hidden layers, and maybe it'll get better, maybe it will get worse. We don't have a very clear understanding of exactly what makes a good or bad architecture. Okay, how is this related to AI? Just at a glance. So AI is a weird thing. AI, when we talk about artificial intelligence, you know, I mean, how do we even define what intelligence is? That's a weird thing, right? Like, and what is consciousness? We don't even know where consciousness stems from. Is it a real thing? Is it an illusion? I mean, these are like philosophy questions, which I'm not even going to try to answer. But you know, as far as computer AI and stuff like that, you know, some of it, okay, and this is what neural networks would fall under, is just given some inputs, make a decision, right? In our case, given a picture of the number 3, can you tell me what digit this is? And if the computer says, hey, that's the number 3, we can say, oh, that's a little bit of AI. That's all we're trying to do here, okay? And we're gonna achieve that using a neural network. And, you know, and that at its root, which is, you know, taking an image and tell me what you see in the image, is this is a very simplified version, again, because it's the data is very clean. It's just black and white numbers or grayscale numbers, and the answer is either going to be 0 through 9. There's only 10 possible choices here. So it's a very, very simple setup, but still the idea of like, can you write a program that where if I give you a 28 by 28 image, it's going to tell me what number it is? Like, prior to neural networks, I'm not sure what approach you would use, right? I mean, there are approaches, but part of machine learning is just kind of this task of taking in the data and reporting what it is, okay? And then as we, and really, the most complicated AI things, like driving a vehicle, okay, self-driving vehicle, is just this, but taken to a very complicated level. Here's an image of the street right now, and please tell me what's in it. Are there other cars? Are there people in the street? Okay, and so that's going to be part of the thing. Okay, just recognizing the objects that are inside the image. And then from there, what is the next correct decision to do? Do I continue driving? Do I apply the brakes? Do I turn? Things like that. That's the other part of the decision making. But but that's what it comes down to. And for a long time, this idea of having, seeing an image and recognizing what it is, this phenomenon, or ability that we call vision, you know, for a long time was thought to only be reserved to basically biological beings, right? Like animals and insects and people and stuff like that. And we didn't think computers were capable of this, but clearly it is, right? Every time you take a picture now, your phone is starting to tag it with all sorts of things, and it guesses what's in there. And now you have these, right? Your phones have these automatically created albums that have said like, hey, here's all the pictures you have with this person's face in it, right? Which is a little bit, I think when it first appeared, it was a little unsettling, but I think now we've accepted this and just say, oh yeah, this is a feature that I want, okay? So anyway, this is what our neural network is going to look like, okay? Now we have 10 nodes in the output layer. Why do we have 10 nodes in the output layer? Okay, well, what we have is each node corresponds to a digit, okay? So let me, I'm going to just keep playing this video because he does a great job explaining
Has
it.
10 neurons, each representing one of the digits. The activation in these neurons, again, some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. There's also a couple layers in between called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons. And admittedly, that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure and...
Okay, but anyway, what we have is we're going to have a node for each digit, okay? And these nodes represent basically whether the neural network believes which digit it is, okay? 6, 7, 8, or 9, okay? And so if the network thinks it's a 7, well, actually, so if the believes it is a 7, the answer, so with the 10 nodes, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, okay, what we want to see, okay, we want to see something like 0 0.00, 0 0.01, values close to 0, 0 point, you know, for everything, for all the nodes other than 7. For 7, we want something like 0.99. This is what we want, okay? Now these nodes don't, this is not a probability distribution. They don't have to add up to 1, okay? Okay. This is not a probability distribution, okay? The values do not add to 1. Okay, but basically what we want is this one, we want close to 1. And then all others should be close to 0, okay? Okay, that's what we want our neural network to output, okay? So this is what we're going to do, all right? And so the neural network that we set up for taking in the hours of sleep and hours of study and outputting a exam score is pretty much going to have the same structure, and that code was going to work fine. We just have to change it to say the output layer has 10 nodes, okay? And those things will be a value between 0 and 1, okay? And I've already posted the code to get this to run, so you can try downloading these the R code here, okay? And you need to download the handwritten data, okay? And so this is the original data set, okay? If you search for Mnist, like there are people who've like converted this thing into like CSV files on Kaggle and stuff, but don't, this thing is a mess, okay? So just a warning, like I think Kaggle is great. There's some really great data sets, but there's also a lot of junk data sets, right? So some people have done like web scraping and put the resulting scraped data onto Kaggle. Now, web scraping is a totally fine way to collect data. That's fine. But there are lots of ways to do web scraping the wrong way, okay? And so, you know, if you just create this simple spider that starts at a link, follows a link, and then scrapes the data, and then follows a link and scrapes the data there, it's probably going to be a junk data set because you might end up in loops and you might get duplicates. You might run the scraper like on multiple days and get different, you know. And there's a lot of ugly, messy data sets on Kaggle, you know, with a lot of duplicated entries and things like that. And so just be careful. Not all data sets on Kaggle are good, okay? Just be careful. But anyway, this is a good data set. You'll have to download these 4 files, and then you've got to unzip them somewhere. Okay, and so on my computer, I've created a directory called Mnist, where I've so the files come in these .gz archived files, and you've got to un-gz them. It's like zip, but like a Unix thing, okay? I don't know what gz stands for, but you got to like expand them out, okay? And so you now get these IDX3 ubyte files, which you can't really do anything directly with, but you can load it up in R, okay? And so, so I've included a file that will load up the data, okay? And so this will, what this will do is it will read in these files here, and it will, basically it reads the binary file, okay, and creates objects in R for us, okay? So so I have posted these 2 files, handwriting.r, which is used to load the data, and then handwriting.ann, which has the neural network, the artificial neural network setup and just regular R code. So you don't have to understand the handwriting.r here, but basically, set your working directory to your Mnist folder where you've got your data. You might have to adjust your the file paths here if you need to, and then I'm going to go ahead and just load these functions into load the functions into R. Okay, and so now I have these two functions here, and I'm going to use that to just load up the data. Okay, so when you call load Mnist, which is a function, it's going to go ahead and load the data. And it's a fairly big file. It's like it takes up 188 megabytes in memory. Okay, and it's a list with a bunch of stuff here. Okay, and so what train is, all right. So if you look at the structure of train, okay, there are 3. It's a list of 3, and the second element is the training, the X, and then the Y is the label. Okay, so you can see we have 60,000 images inside train. Train X will be is a matrix, 60,000 rows, 784 columns. Each row is 1 vector of all 784 pixels, right? So we've taken the image and we flattened it, stretched it out into just 1 vector of 784 values, and so each row inside training $X is the digit as 784 values, right? So the and then Y is just a vector of the labels, okay? So here, this is the label. The label is 5, and the vector of 784 values is this, okay? So the vector of 784 values is this. Now, if I were to arrange this into a 28 by 28 grid, then it will look like a digit, okay? So zeros mean, there's no ink applied, okay? And values near 255 would be means somebody wrote there, okay? So my pictures are black and white, or black ink on a white background in Grant's video. Uh-oh. Oh no, my computer just froze. Okay. So in Grant's video, he has it a little bit. He has it the other way. He's got. Okay. All right, my thing just broke. Oh boy. Okay. I have to stop. Let me